Now I want to use a diode in a circuit, and we'll see how we solve circuits that include these nonlinear diodes in them. So I have a circuit here with a battery and a resistor and a diode here, and it's going to be a special kind. It's going to be an LED diode. So it's going to give off light. This is a kind of diode that's manufactured to generate photons of light when it has a current flowing through it in the forward direction. They're pretty cool, and you see them all the time in electronic components. So we're going to figure out how to use an LED in a real simple little circuit. And in our circuit here, we're going to have a resistor of 330 ohms, and we'll make this battery 3 volts. So it's like 2 AA cells. And what we want to find out is how much current is going to flow around this circuit. And let me label this here. Let me label the voltages across our components. We'll have VD, which is this voltage here. And we'll have VR, which is the resistor voltage, and that's that voltage right there. So now I'm going to show you a plot of the IV curve of our diode. You can see right here around 0.7 volts, the current rises rapidly when there's 0.7 volts across the diode. And let's start out by analyzing this. Let's start with the same tools that we always have, which is let's try to write some current laws for these two things. So for the diode, we write a current law that looks like this. The current is equal to IS times e to the q v on kt minus 1. So that's the IV characteristic for the diode, where this is V diode right there. And the corresponding equation for the resistor is I equals V resistor over 330 ohms. That's just Ohm's law for the resistor. And I, in both cases, is this I right here. Now, if I wanted to, I could set these two expressions equal to each other and solve somehow for VD and VR. But what we're going to do instead is we're going to solve this by graphing, by a graphical method. Here's a graph of the diode, and this is the VD scale. This is V diode, and this is I up here. And so what I want to do is I want to plot the resistor curve on here as well. I want to plot the resistor IV curve on this same plot. Now, in this expression, I have VR instead of VD. So let me see if I can work on VR here. Let me try to figure out VR in terms of VD. So I can derive VR as 3 volts minus VD. And let's put this into this I expression here. The Ohm's law expression now becomes I equals VR is replaced with 3 minus VD all over 330 ohms. And let's work on this a little more. I equals 3 over 330 minus VD over 330. And this is starting to look like the equation of a line. Let me write this to recognize it as an equation of a line. Minus VD over 330 plus 3 over 330 is 9 milliamps. So this is the equation of a line, and the slope is right here, is minus 1 over 330, and the I-intercept is 9 milliamps. So let's see if we can plot this line. This is actually called a load line. That's just a nickname for this kind of expression that you get when you have a resistor, connected to a fixed power supply above, and the resistor is hanging down from it. You get this characteristic equation of a line that has a negative slope, which is really distinctive. Let's see if we can plot this line. Now, it's a line, so all we have to do is find 2 points that solve the line, and then we'll be able to draw the line. So if I set VD equal to 0, then I equals 9 milliamps. So here's VD equal to 0, and it'll go through 9 milliamps. So that's 1 point on the line. But what else can I set to 0? I can set I equal to 0, which means I'm on the voltage axis. And what I'm actually going to do is I'm just going to look at my circuit and figure this out in my head. So I'm setting I equal to 0, and I equals 0 means there's no current in this resistor, which means there's no voltage drop across that resistor. And that means that this voltage here is the same as this voltage here. And I know the voltage here. The voltage here is 3 volts. So that means the voltage here is 3 volts. And that's because I know the current is 0. So let's go over and put that point on our line. So when I is 0, V is 3 volts. So there's another point on the line. And now we have 2 points, and we can draw a line between them, like that. And what we've drawn is the load line for this 330 ohm resistor. You remember back over here, we said we could solve these two equations by setting the two I's equal to each other. And that's basically, where do these two lines intersect? And they intersect right here. That's the solution to our problem. So this intersection point is the solution. It's where the resistor current and the diode current are the same. And that's that point there. And now I can just read off my answer. Right there is about 0.7 volts. And the current over here, if I read off the current, just straight across there, it's about 6.8 milliamps of current. So now we actually just solved our circuit using a graphical technique. And what that says is, here, let me erase this a bit to clean it up. Let me take out these two things here. That was just the resistor load line that we were talking about. And now for our solution, we have I equals 6.8 milliamps, and V diode equals about 0.7 volts. So that's how you do a graphical solution with a diode.